So we have talked about ocean heat uptake already several times. We are revisiting that in this specific context of the mean state of the tropical Pacific and the response of the tropical Pacific to anthropogenic forcing. When we say anthropogenic forcing, it's always about radiative perturbations because of anthropogenic activities like increasing greenhouse gases, urbanization, deforestation, cement production, land use change, and so on and so forth. And we looked at this kind of a trend plot already several times as well. We said when we look at anomalies with respect to some base period like the 20th century or 1961 to 1990, which is more typically used also, we were below that. Here it is 1901 to 2000. We were below that before about 1940, and then we started jumping around it, and then since about 1980 we have been increasing quite rapidly, and we saw that the warming rates are accelerating. But we also talked about how there are year-to-year variations because of natural variability, and because the energy also goes into evaporation, glacier melting, and so on. Here is my chopper back on its way again. I have no idea whose chopper it is and where it goes, but nonetheless, if we look carefully here, the warming rates are not always constant, and that is shown more specifically here. So this is from this article from The Conversation. There has been a controversy or debate over the last 15 years or so, where some people noticed and argued that maybe the global warming rate flattened after about 2000 or so till at least about 2012, 2013, and then there's been a debate about whether that was really a slowing down, whether there was really a pause in global warming, or whether it was a problem with data, and so on and so forth. But we have already talked about how volcanic eruptions can produce temporary dips in global cooling, can create temporary dips in global warming because of the global cooling effects. And the other controversy was that the global climate models, which are used for IPCC projections, can do pretty well in reproducing the trend of warming because of greenhouse gases, solar forcing, volcanic forcing, and so on, didn't capture the change in the rate of warming during this period that is in this gray band here. So that was called global warming pause, because the warming rates slowed down, even though some people argue that it didn't happen. What is the relation to El Nino and La Nina? So we already saw the mean temperatures. So we have cold temperatures because of the upwelling of the South American coast along the equator towards the dateline, which we call the cold tongue, and we have the warm pool on the other side. And we said this is caused by Ekman divergence, upwelling, and so on. Why is it critical? Because it turns out that I put these in wrong order. It turns out that where the cold water comes up because of ocean dynamics and Ekman divergence, the atmosphere dumps a lot of heat to try to cool those temperatures. This is how the ocean atmosphere interactions work. So there is more than 200 watts per meter squared of average heat flux trying to go into the ocean here, because the ocean is cold, whereas you can see that where the ocean is warm, there is very little heat going in. There are other places where in the tropics where here also we have upwelling. So India, tropical Pacific and Atlantic oceans are similar. Indian Ocean is different because of the monsoonal forcing, and you can also see Benguela upwelling and Peru upwelling take up heat as well. And where there are western boundary currents bringing heat from the tropics into higher latitudes, like the East Australian current, Brazil current, and the Gulf Stream, atmosphere picks up the heat from the ocean. So warm waters are coming to these regions from the western boundary current transports. Atmosphere is colder and ocean is losing heat, which is obviously critical here because that is part of the evaporation and cooling which creates North Atlantic deep water in these regions, Labrador Sea and Jin Seas that we talked about before, as well as here Brazil Malvinas current and East Australian current. So this is kind of the long-term balance where ocean is taking up heat in the lower latitudes and it is losing heat and these mid-latitudes and higher latitudes. Okay, so this balance can be affected on a trend sense, on a global warming time scale, if these temperatures begin to warm. If these temperatures in the East Pacific warm, then the heat uptake from the atmosphere will be reduced, which means, remember, the ocean heat uptake can stay down for a long time because it has a long heat high heat capacity, and thermohaline circulation is a long-term phenomenon. Once heat goes away from the surface, it cannot be exchanged very quickly with the atmosphere. So that stays in the ocean for a longer time. Of course, it gets released, some of it gets released during El Nino as the warm waters are spread out and the ocean gives back some heat, causes actually a temporary global warming during El Nino. So that's what we were talking about before. If this region in the West Pacific warms faster than the East Pacific on a multi-year, multi-decadal time scale, then this ocean heat uptake will continue, plus it will create anomalously high pressure and anomalously low pressure. So the wind response from high pressure to low pressure will amplify this less warming in the east. So you have to be very careful. There is the upwelling that is seasonal, there is the upwelling on a long time scale. So the trend in upwelling versus seasonal and interannual variability in upwelling is what we are talking about. So the positive feedback on a trend time scale is that if the East Pacific doesn't warm as fast as the West, then the sea surface temperature gradient and the pressure gradient can amplify this pattern of less warming in the east and more warming in the west, which is good because ocean will continue to take heat uptake and then that will modulate the warming, which is what the warming pause is. So the main argument made was that if we look at the trend of temperatures, we said it is warming less here or maybe even cooling compared to the west, which explains why we could have had a global warming pause. Okay, so that's the main idea for looking at El Nino and trying to understand. So ocean heat uptake works this way. There is short wave coming in, the longer wavelengths penetrate the ocean and ocean reflects long wave, obviously sigma t to the fourth. Any body that warms has thermal radiation, heat radiation. There is evaporation and latent heat exchange between the ocean and the atmosphere, which is very critical part of the energy pickup from the atmosphere and northward transport. And there is sensible heat, which is related to the temperature difference between the ocean and the atmosphere. And there are other fluxes like freshwater flux and momentum flux and so on and so forth. So looking at this, then the question is, with global warming, is the heat going into the ocean decreasing? Is the pattern of warming looking like it's less here and more there, which would adjust also the heat losses here, which would affect the thermocline depth here, because how cold the temperatures get and how much ocean can take up the heat depends on how shallow the thermocline is. So if you change the heat uptake here and heat loss here, then the entire ocean adjusts on multi-decadal timescales, because it takes a long time for the water that is upwelled here, moved westward and poleward, to make it to this far and then adjust the whole system. That's part of the oceanography as well, but we didn't get into those kinds of details. So just remember that El Nino pattern gives us a sense of how ocean uptake affects global warming. When we say global warming, it's always atmospheric temperature, right? So atmospheric temperature is the rate of warming. Obviously depends on how the excess energy being trapped by increased greenhouse gases and other activities, the delta F, the radiative forcing that we talked about, how that excess energy is being distributed. We said ocean takes up 93% of it, but where does it take up? Tropical Pacific is one of the critical regions. This is why we need to learn about El Nino as a one of the processes that's critically involved in this. Plus, as I mentioned, during an El Nino there is a mini global warming. Global average temperature goes up because the ocean spits out some of the heat it accumulates during normal times with upwelling in the east, or during La Nina times when the upwelling in the east is stronger than normal. So that ocean uptake in the tropical Pacific modulates global warming, or how quickly the atmosphere can warm, because the uptake of heat by the ocean can reduce the warming rate. There are many details. It turns out that the uptake of the heat by the Pacific is also affected by the warming that's happening in the Indian Ocean. It's affected by other places like the Atlantic as well. But just remember that the warming pattern has this polar amplification, which is real and true, but just this tropical Pacific part is still very critical. Okay.